me. 6-day online faculty development program on navigation with Indian constellation, opportunities, challenges, and future developments, hosted by the Department of Electronics and Communication Engineering of our college, Saranathan College of Engineering, Tiruchirappalli. Our institution holds a distinguished legacy, founded in the year 1998 by our revered founder secretary, Vidya Sevaratnam, Guru Sevamani, Auditor Sri K. Santanam. As a mark of deep respect and gratitude, our college carries the name of his guru, the legendary scholar and former principal of National College, Professor V. Saranathan, whose contribution to education remains monumental. Today, Saranathan College of Engineering stands as a leading center of technical excellence in this region, committed to quality education, discipline, values, and innovation. With this proud heritage and academic vision, we are delighted to host this knowledge enriching FDP, exploring the technological depth, opportunities, and future scope of India's indigenous satellite navigation system, NAVIC, NAVIC. To begin this auspicious academic gathering with divine blessings, I request everyone to remain composed for the invocation prayer.
यो देवश्रुतिसेकरेषु विदितः यम्बासकं जानते येन भ्राम्यति लोकजालमखिलम् यस्मै नमस्कुर्वते यस्मानां परमस्ति किञ्चिदपि वै यस्याङ्गं भूतं जगत् यस्मिन् तिष्ठति सर्वमेव भुवनम् कुर्यासनो मङ्गलम् நீராறும் கடலுடுத்த நிலமடந்தை கெழிலொழுகும் சீராறும் வதனமென திகழ்பரத கண்டமிதில் தெக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரிதனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே முன் சீரிழமை திறம்பியந்து செயல்மறந்து வாழ்த்ததுமே வாழ்த்ததுமே வாழ்த்ததுமே.
Thank you all. Now, it's my privilege to invite our beloved professor and head of the Department of EC and convener of this FDP, Dr. M. Shanti Madam, to welcome the gathering.
Good evening, everyone gathered here. Honorable Secretary Sri S. Ravindran sir, respected Principal Dr. D. Valavan sir, respected Head R&D Dr. R. Nadarajan sir, distinguished Chief Guest of today's function, Professor P. Soma, former Deputy Director, ISTRAC ISRO, heads of various departments, my dear colleagues, faculty members, research scholars, PG students, and participants from various institutions, ladies and gentlemen. A very warm welcome to you all for the 6 days online FTP program on navigation with Indian constellation, opportunities, challenges, and future developments. With the blessings of our founder secretary, Vidya Sevaratnam Guru Sevamani, Auditor Sri K. Santanam sir, our institution has successfully completed its 27 years of academic journey. Now, I want to tell something about the topic of the today's FTP program, navigation with Indian constellation. The Indian Regional Navigation Satellite System, IRNSSS, also known as the Navigation with Indian Constellation, is an independent, standalone, indigenous navigation satellite system developed by ISRO. It will be under the complete control of India, with the space segment, ground segment, and user receivers all being built in India. IRNSS establishes a regional navigation satellite system using a combination of geosynchronous orbit and geostationary orbit spacecraft and state-of-the-art ground systems. IRNSS NAVIC is designed to provide accurate position information service to users in India and the region extending up to 1,500 km from its boundary, which is its primary service area. NAVIC is designed with a constellation. NAVIC is designed with a constellation of 7 satellites. 3 satellites are placed in geostationary orbit (GSO) and 4 satellites are placed in inclined geosynchronous orbit (GEO). The 7 satellites, the NAVIC constellation so far use 2 frequencies. One is L5 band and S bands. The IRNSS system is expected to provide a position accuracy of better than 20 meters in the primary service area. Some of the challenges are failure of imported atomic clock, launch issues, limited coverage, device adoption and awareness, etc. Future development include launching a series of new satellites with indigenous rubidium atomic clocks, addition of L1 frequency band, increasing the constellation size to 24 satellites to increase coverage, integration with 5G, etc. Some of the objectives of ATAL Academy are to impart quality technical education in the country, to foster research, innovation, and entrepreneurship through training, to empower technical teachers by training and exchange of experiences through organizing workshops, orientation programs, and other faculty development programs. At this moment, I would like to express my gratitude to AICT Chairman, ATAL Coordinator, Selection Committee members to provide an opportunity for us to organize this 1 week online ATAL FDP program on navigation with the Indian constellation, opportunities, challenges, and future developments in our college. At the outset, it gives me an immense pleasure to welcome the chief guest of today's function, Professor P. Soma, former Deputy Director, ISTRAC ISRO, who has kindly accepted our invitation to deliver a lecture. Thank you, sir, for magnanimously accepting our invitation in spite of your busy schedule and sparing your valuable time with us in knowledge sharing. Our hearty welcome to you, sir. It is my honor and privilege to welcome our Honorable Secretary, who has magnanimously accepted our proposal to organize this FTP program and motivating us to organize many such programs in our institution. I am very much delighted in welcoming our principal, who immediately sanctioned and recommended our request to Secretary Sir in applying for this FTP program and provides constant support and suggestions towards this event. Our sincere welcome to you, sir. I extend a hearty welcome to our head R&D, who guided us a lot in all aspects and provided suggestions towards this program. Our hearty welcome to you, sir. It's my pleasure to extend a cheerful welcome to heads of various departments who supported us by motivating their faculty members to attend this program. I am very happy to welcome my colleagues who are supporting us in organizing this function a successful and memorable one. I am very much enthusiastic in welcoming all the faculty members, research scholars, and PG students from various institutions without whom the function would not have been a successful one. I would like to share that 185 participants are attending this FTP program. We are very grateful to the resource persons who magnanimously accepted our invitation to deliver the lectures in this FTP program. The resource persons are Professor P. Soma, former Deputy Director, ISTRAC ISRO, Dr. Ashish K. Shukla, Head Advanced Navigation and Science Applications Division, SCSC ISRO, Mr. G. Bharatidasan and Dr. S. Pratibha, Akkad Software and Systems, Bangalore, Dr. G. Raju, former Project Director, ISRO, Professor, Jain University, Bangalore. Dr. D. Venkataratnam, Professor, KL University, Andhra Pradesh. Dr. Anindya Bose, Professor, the University of Burdwan, West Bengal. Dr. B. Naveen Kumar, Professor, Osmania University, Hyderabad. Dr. A. Supraja Reddy, Associate Professor, CBIT, Hyderabad. Dr. A. Sarkar, DRDA, Hyderabad. Dr. S. Ramesh Raju, Senior Manager, Honeywell, Bangalore. Dr. Kavita Devi Reddy, Research Associate, Manjira Digital Systems, Hyderabad. Dr. Punyavi, Associate Professor, King Mongoose Institute of Technology, Thailand. Dr. Sarath C. Das, Professor, Ayatwat University, Malaysia. So the above resource persons are magnanimously accept our invitation to deliver the lecture in our FTP program. We are thankful to them for sparing their valuable time with us. I expect every participant to fully involve in the program and benefit out of it. I would like to conclude my address with a famous quote by Dr. APJ Abdul Kalam. Learning gives creativity. Creativity leads to thinking. Thinking provides knowledge. Knowledge makes you great. Once again, I would like to extend a very warm welcome you all for this 6 days online ATAL FDP program. Thank you.
Thank you so much, madam.
Thank you, sir.
Warm welcome and setting. We are honored to have a respected principal whose leadership continues to strengthen and elevate the academic standards of our institution. May I now invite you, sir, to deliver the presidential address.
Professor Soma sir has joined. Welcome you, sir.
Welcome, Professor Soma. Very good evening to professors, distinguished chief guest and keynote speaker for the first session, Professor P. Soma, former Deputy Director, ISRO, Head R&D, Head of the Department of ECE, Dr. M. Shanti, Program Coordinator, Dr. R. Mukesh, faculty members, and participants. It gives me a great pleasure to extend to you all a very warm welcome on behalf of Sarnathan College of Engineering, Trichy, and to say how grateful we are to the resource persons who have accepted our request to deliver keynote address in this 6-day ATAL online faculty development program organized by the Department of ECE. I appreciate the Department of ECE in general and Professor Dr. R. Mukesh in particular for identifying the resource persons from great institutions and for other arrangements. I wish this online ATAL FTP be successful and reach its goal as expected by all. And I wish you all to have an enjoyable learning days. Thank you all. Thank you.
Thank you so much for your inspiring messages. Thank you. We are also privileged to have with us our beloved head R&D, Dr. R. Nadarajan sir, whose rich academic and industrial expertise adds immense value to this program. May I now request you, sir, to offer your felicitation.
Thank you. Thanks for the introduction. And at the very outset, so good evening, everybody, those who are virtually connected to this FDP. At the very outset, I would like to congratulate the organizing committee who have put in a lot of efforts in bringing very resourceful resource persons for this. Today's keynote speaker is deputy director from ISRO. So it is I would say, the constellation of resource persons is an exceptional constellation, and I wish them all the success so that they have a very fruitful FDP for all the 6 days. NAVIC, the Indian navigation with the Indian constellation of satellites, is a very prestigious project by ISRO. And as it is always, this project also is by ISRO is achieved at a very, very low cost comparing to the other similar systems all over. I would even say that the amount of money spent on this project is 174 million, which is less than 50% of the budget of Avatar 2. So that is the hallmark of every project undertaken by ASRO. And being proud Indians, we should always be proud about whatever is achieved by ASRO and ASRO scientists. And more than this, the price, the NAVIC offers 2 services. One is for the defense. For the defense services, the accuracy is 5 meters, whereas for the general public, the accuracy is 15 meters, which is far less than what is offered by GPS of USA, which is 20 to 25 meters. And similarly, it is more accurate than the Galileo offered by European Union. And more than this, GPS, the US navigation system, it has 31 satellites. It's a constellation of 31 satellites. And every year, one satellite becomes dead and they have to replace it. And that is not the case in our system. So I would again say that as proud Indian, we should always have a head up. And then we can say that Mera Bharat Mata. And this ATAL FDP is going to cover the challenges, the opportunities, and all the future developments of NAVIC. So after listening to these 6 days, I think every one of you, all the participants will have very fruitful, interactive sessions so that they will all be better informed than what they are today as far as NAVIC is concerned. And I would also like to say that one of the challenges facing NAVIC is to develop a receiver chip. Already iPhone 15 Pro and iPhone 15 Pro Max, they are able to receive the navigation by the NAVIC. They are able to receive the signals from NAVIC. But whereas any of our Indian things are not able to do that, and that is the main challenge, I would say. So I would say that by 2026 or by the end of every one of us will be having a smartphone that will be using NAVIC, or we are able to get the NAVIC. And I wish you all the best, and I wish the organizers all the best, and I wish every one of you a very, very high level interactive FDP. And thank you very much for this opportunity, and have an excellent evening. Thank you very much. Thank you. Thanks, everybody.
Thank you so much, sir. Thank you for your encouraging and insightful words. We are honored to have with us Professor P. Soma, a visionary aerospace expert with over 36 years of pioneering service in ISRO. Sir's contributions span India's space missions, including Apple, Bhaskara, IRS series, ISRO's Gaggan, and IRNS's NAVIC program, where he played a key role in establishing mission operations, ground infrastructure, and satellite control systems. Sir has represented India globally, worked with European and German space agencies, and has delivered invited talks on orbit determination and mission analysis internationally. After retiring from ISRO, Sir continues to inspire young minds as Professor of Eminence in Aeronautical Engineering, nurturing research in satellite navigation and ionospheric modeling. With more than 70 technical publications, multiple awards, including the ISRO Team Excellence Award, and a legacy of contribution to Indian space technology, Sir remains a respected authority in satellite navigation and mission operations. Professor Soma served in Indian Space Research Organization ISRO across several key divisions and played a crucial role in conceptualization, development, and deployment of systems related to India's satellite navigation program. His expertise spans NAVIC system architecture, signal design, receiver development, and satellite communication technologies, making him one of the foremost resource persons in this domain. With his deep technical knowledge, decades of hands on research experience, and his ability to translate complex engineering concepts into practical and relatable understanding, Professor Soma continues to mentor researchers, engineers, and academicians across the country. He has contributed to numerous national initiatives, publications, workshops, and knowledge building platforms focused on navigation with Indian constellation.
Yeah.
Today, we are fortunate to have him share his insights on NAVIC, its relevance, evolution, technological strengths, applications, and the road ahead. With great pride and privilege, let's warmly welcome Professor Soma to inaugurate and lead us in today's technical session. Please, sir.
Can I go ahead?
Good evening, sir. Yes, sir. Please, sir. Your screen is visible, sir.
Good evening, everyone. Thank you, Dr. Mohan, for your kind words of introduction of me to the audience. Let me at the outset thank the principal and the organizers of this ATAL Faculty Development Program 2025-26 and the management of Saranathan College of Engineering and Institution of Excellence at Trichy. Greetings to all the participants. It's a pleasure to be with you today and take you on a journey not just across space, but across the hidden science that quietly powers every space vehicle mission we have ever launched to travel safely from Earth to space and even to other planets and sun. My today's presentation is titled Navigation in Space, the Indian Perspective. You may have heard the line before, rockets take us up, but navigation takes us there. That is exactly what we will explore today. Let me get into a slideshow mode. Okay. Rockets takes us up, navigation takes us there. I have divided the presentation into 4 parts. Part 1 is an introduction, essentially defining what navigation is and why space navigation matters. And part 2 deals with the basics for navigation in defining coordinate frames of reference, timing systems, and also navigation data measurement techniques and methods. In part 3, we go through India's navigation history and achievements. Here, we will discuss historical missions, indigenous developments, India's advancements and achievements in this area, We'll also cover what is called the IDSN, Gagan, Navik, Chandrayaan, Mangalyaan missions involving precise navigation schemes. I'll explain all these things in detail. In the last and the fourth part, we will address the challenges, future directions, and wrap up with some conclusions. So, the first part, introduction, why space navigation matters. When we travel on Earth, navigation seems very simple. We have maps, we have roads, GPS system, street signs, and so on. So it makes life simple. But imagine navigating in space where there are no roads, no fixed landmarks, and everything is in motion. All planets are moving, solar system, is moving in galaxies and so on. Space vehicles must travel lakhs of kilometers, sometimes crores, and still hit a target the size of a football field very precisely. A 1 degree error at launch, a degree alignment error at launch can grow into thousands of kilometers by the time you reach the deep space. Navigation is what keeps the missions alive, from Chandrayaan landing on the moon to Mangalyaan orbiting Mars to Aditya L1 holding its position 1.5 million kilometers away. So without much ado, let me explain to you what navigation is. So what navigation is? Navigation is to know where you are in three-dimensional space. Your coordinates are position as latitude, longitude, or altitude, or XYZ in Cartesian frame of reference. Also, how to go, where you want to go, which is your destination. So these two things are involved in navigation. So the navigation information is P, V, and T, position, velocity, and time. So the navigation systems are also known as PVT systems as they provide position, velocity, and time. So navigation is how a space vehicle or spacecraft knows its position and velocity at every instant of time, and it allows, therefore, precise orbit insertion, attitude control, docking, and landing, and so on in its mission. At the core of every space mission lies CNG, the so-called CNG, command, navigation, and guidance. A little bit technical. Among these, navigation is the backbone. Without knowing exactly where a space vehicle is, commands are meaningless and guidance laws fail. Navigation, therefore, is the most invisible, indispensable system in a space flight. Navigation decides mission success or failure, therefore, it matters and therefore it is critical. So, PVT system, where you are, how to go, where you want to go. So, this is what is the navigation is about. Now, let us now look into some more basics for understanding navigation in terms of the frames of reference, timing and navigation measurement techniques in a simpler manner. Let us talk about coordinate and timing systems first. Space navigation depends equally on two things: where we measure and when we measure. For where, spacecraft uses various coordinate systems. Where means position. To navigate in space, we need reference frames or coordinate systems. There are two important coordinate systems which we use when we are on the Earth or with respect to the Earth. The first one is the ECA frame. ECA stands for Earth-Centered Inertial Frame, a spherical coordinate system which is for stable reference. The origin is at the center of the Earth. X-axis points towards vernal equinox, direction of vernal equinox, and Z-axis is along the pole rotation axis of the Earth, and the y-axis is on the equatorial plane, which is the reference plane. This ECA frame is required for modeling the motion of the spacecrafts, satellites, and other celestial objects. On the other hand, we have the ECEF frame, Earth-centered, Earth-fixed frame. ECEF is Earth-centered, Earth-fixed frame, which rotates with the Earth, whereas ECA frame is inertial in space, is fixed in space. Origin is at the center of the Earth, x-axis on the equatorial plane on the Greenwich meridian, z-axis towards the North Pole, and y-axis on the equatorial plane forming the triad. This system is useful for describing vehicles on or near Earth's surface. So there is a comparison table, and which also gives the use. ECA is used for modeling the motion of spacecraft, satellites, and other celestial objects. ECEF is used for describing positions on or near the Earth's surface for applications like navigation and surveying. So, Earth rotates while the celestial sphere appears fixed. In the first case, the Earth is stationary while the celestial sphere appears to be rotating in the case of Earth-centered, Earth-fixed system. You can visualize this. Okay. For this, there are other two systems which we talk about now. The celestial reference frame, such as a planet and solar system frames, are used. Frame here means coordinate system frame, are used for deep space missions. So when you go for deep space missions, we have to use solar system frame or celestial reference frame. For lunar missions, moon-centered inertial frame is used primarily for modeling the orbits and trajectories near the moon. Okay. The solar system, barycentric is frame is a coordinate system with its origin at the solar system's center of mass. So it's not at the center of the sun, it's at the solar system center of the mass, also known as barycenter. This is an inertial frame which does not accelerate with reference stars, and it is most stable reference frame for studying the motion of the objects within solar system. For interplanetary missions like Mangalyaan, we switch from Earth-centered to Sun-centered to Mars-centered frames. For Chandrayaan, we switch from ECI frame to lunar-centered frame, as you can see on the right side of the view graph. Now, for when, the answer lies in atomic time. For where, we talked about the coordinate frames. For when, the answer lies in the atomic time. Time has to be measured accurately, as accurate as nanoseconds. 1 billionth of a nanosecond is 1 billionth of a second, and hence requires atomic clocks. Even millisecond accuracy is not adequate for space navigation. For Near Earth satellites move around 7.5 to 8 kilometers per second, and interplanetary spacecraft travel at 10 to 30 kilometers per second. This is to give you an idea. Since light travels at 300,000 kilometers per second, 1 millisecond error in measurement of distance from the Earth gives roughly 300 kilometer error. 1 microsecond gives 300 meter error, and 1 nanosecond ends up with 30 centimeter positional error. Over months, interplanetary travel, small timing errors grow exponentially. As a result, trajectory can drift by hundreds or even thousands of kilometers. Therefore, it is very essential to have the time measured very accurately, both on the ground and on the spacecraft. Therefore, atomic clocks with nanosecond accuracy are essential for space travel and navigation. Accurate time, I would say, is the backbone of navigation. So, a little bit more on timing and measurement system. Atomic clocks on board satellites and ground stations ensure precise timing, which is crucial for accurate navigation calculations. Each one of the NAVIC satellites, our own satellites, for example, are equipped with rubidium clocks, which are balanced for accuracy, compactness, and cost effectiveness. Rubidium clocks are little inferior in time keeping. Atomic clocks used on the ground segments are ensemble of cesium clocks and hydrogen measures. While rubidium clocks are used on the satellites, on the ground, we maintain a timing system using cesium clocks and hydrogen measures. Timing center at Bairalu is an important part of the NAVIC ground segment, for example. So, these systems, these clocks can maintain time to an accuracy of 1 nanoseconds, 1 to 10 nanoseconds, let us say. Now, let us look at, we have looked at the coordinate system. We have looked at the timing system, the importance of maintaining good time on the atomic clocks, which are used for this purpose. Now, let us look at the measurement techniques. It's a very involved scheme of things, but let me simplify it for a quick understanding. The measurement techniques used are, on the right hand side, you have two-way ranging. Ground stations send a signal to the spacecraft and receive it back from the onboard transponder. Transponder is a device which transmits the signal back. And the time difference or time delay between the sent and arrival times of the signal multiplied by the speed of light provides twice the range value. Range is the distance between the object, space vehicle, and the ground station. 1 nanosecond is equal to 30 centimeter error. That's what he has said. And therefore, the range, if it has to be measured accurately, the timing has to be very accurate. Apart from range, when we send signals and receive them back, there is a Doppler shift in the signal, which is also measured. The Doppler measurement, gives the range rate, how range is changing with time. Doppler measurement is used to determine the velocity of the spacecraft related to the tracking station. And in interplanetary space missions, a special technique called delta DOR technique provides centimeter level measurement precision in determining the spacecraft position, even millions of kilometers away. Here, two widely separated stations track the spacecraft using the background quasars. Quasars are used for this purpose. I encourage the listeners to study in detail about these radio frequency based tracking systems which is a subject by itself, as well as optical or laser ranging systems. So navigation measurement techniques are many and used depending upon the mission phase. Every mission has got different phase. Satellite mission, rocket mission, launch vehicle mission, okay, and so on. So they can be broadly classified as ground-based tracking, which gives you what I said, ranging and Doppler, using very large antennas and frequencies, and Doppler and ranging methods using radio frequencies, and also expensive laser techniques to obtain very accurate measurements of range and range rate. Autonomous navigation systems involves onboard star tracker, a device which tracks the telescopes that track the stars. Okay, it's called star tracker, and gyroscopes. These are deployed specifically for deep space communication, mainly for deep space communication, blackout phases, and also to be autonomous when the ground station contact is not there. Hybrid system is a combination of these two, ground-based as well as autonomous navigation. Uses integrated ground control plus onboard autonomous systems. Hybrid subsystems reduce delay for interplanetary operations where signal delays can be several minutes, or the order of 10 to 15 to 20 minutes. We'll say that synergy of the instruments enables fuel optimization, which is very, very important actually, which finally defines the cost of the mission, and safe landing and precision control. So we have ground-based tracking, you have autonomous navigation, and we have hybrid systems. Okay. So the onboard sensors, just to give an idea, and tracking infrastructure comprises of radar or laser altimeter, which measure the altitude for landing, star tracker plus gyroscope, as I said earlier, which helps in computation of attitude, orientation, and control. Inertial navigation systems, which is comprising of gyroscopes plus accelerometers, which can give position, velocity, and acceleration, and laser tracking stations along with radio tracking stations, we can give you the range and range rate. We can say that these sensors are eyes and ears, always feeding the navigation brain. If navigation is the brain, these are sensors or the eyes and ears. Now, with this understanding, basics of coordinate systems, of timing system, of measurement systems, let us get into a little more details. India's navigation history and its achievements. The early development of launch vehicles, SLV, which is Dr. Kalam's baby, and ASLV missions that taught us trajectory control. For the first time when you are doing, you have to learn by actually doing things with your own hands and facing a failure as well. The evaluation through PSLV and GSLV PSLV is Polar Satellite Launch Vehicle and GSLV is Geosynchronous Satellite Launch Vehicle, required very accurate position and velocity determination to place payloads or satellites very precisely in their orbit. The INSAT, Indian National Satellite System, widely used for communication systems, communication for the country, and the IRS satellites, which are used for remote sensing applications. Demand, which came in 90s actually, in late 80s and late 90s of the last century, required precise orbital predictions very high orbital stability for communication and remote sensing. Each satellite became a navigation experiment by itself. We have to design transponders, we have to work with the ground stations, we have to compute the orbits, we have to keep them in their place, perform maneuvers, and so on. It's a great, navigation experimental phase, I'll call it. Chandrayaan-1, which came much later in 2008, marked a pivotal milestone in India's space navigation capabilities. It demonstrated first deep space trajectory correction, navigation transition from Earth-centric to lunar-centric navigation. Mangalyaan, which followed this in 2014, took this a step further with navigation transitioning from Earth-centric to Mars-centric navigation. So, for the first two bullets, is a history of more than 2.5 decades of experience of working with navigation systems and perfecting and mastering the navigation requirements for satellites, which are used for communication and remote sensing, as well as scientific missions. I'm looking at indigenous technologies building autonomy. All of us know that GPS provides worldwide navigation system, but it is operated by DoD, can be denied anytime. So we embarked on space-based navigation system for our country. So in that context, we built two space-based navigation system, one which is called Gagan. I'll explain this too in subsequent slides. Gagan is GPS-based geo-augmented navigation, which is meant for air navigation. The other one is the navigation with Indian constellation, India's indigenous regional navigation satellite system. Ensures uninterrupted coverage throughout the region 24 hours a day. We can call this as Indian GPS. No, we'll call it as NAVIC only. Navigation relies heavily on the infrastructure on the ground as well as on the space. And ISRO built its own infrastructure over years. Of course, apart from Gagan and NAVIC, there is ISRO Telemetry Tracking and Command Network, which is the backbone of India's space missions, providing real-time tracking, telemetry, and control for satellites and launch vehicles. ITLAC network handles all our missions. And of course, we also have, as part of this track, a deep space network, Indian Deep Space Network, IDSN, stationed at a place called Bailalu, about 60 kilometers from Bangalore, enables high precision tracking, telemetry communication and ranging with interplanetary missions like Chandrayaan, Mangalyaan, Aditya L1. These systems ensure India does not depend on external tracking for its spacecraft. In the good old days, in our experimental phase, we have to depend on external ground stations for tracking help. That's all in 1970s, actually, when we had Aryabhatta and then Bhaskara. But subsequently, we have built our own ground stations and a network of ground stations, as well as the IDSN. Let me talk a little bit about the Gagan. Gagan is GPS-aided, geo-augmented navigation. It's a satellite-based navigation system developed by ISRO and Airport Authority of India to enhance navigation accuracy over Indian airspace. This is a requirement from ICAO. If aircrafts have to use GPS as one of the aids for navigation, then they have to have an overlay of satellites which can augment the system. It is called satellite augmentation system, and then provide accurate GPS information so that the aircraft can fly safely. It's safety of life system. Gagan using a overlay communication satellites. In the diagram, you can see on the top, 1, 2, 3. 3 of the overlay communication satellites. They are at 36,000 kilometers. And elaborate ground segment. All these have to be built by ISRO and AI, of course, which are coupled to their control center, which you see at the center of the diagram. Improves the accuracy of GPS. The GPS signals as such, one frequency is only allowed on the aircraft. Therefore, the accuracy of, GPS signal is quite bad. And it has to be improved actually, because it suffers 3 kinds of errors. Ranging suffers. One is the ionospheric error, second one is the clock error, third one is the ephemeris error. ICE, I remember it as ICE. Ionospheric, clock, and ephemeris error. And these errors have to be corrected by having your own equivalent of GPS, satellites, which can also augment the GPS constellation, which also augments the GPS constellation, and helps in correcting these errors and providing the range values very accurately. Okay. So when you have a safety of life system like an aircraft using GPS, one has to ensure the accuracy, availability, reliability, and integrity of the system, which a normal GPS system will not be able to do. Therefore, you have to put an overlay of system on the top of the GPS, which also act as GPS satellites, because they have the capability to do the ranging with users on the ground and as well as in the air. To provide more precise and reliable satellite signals for civil aviation, air traffic management, and that's a use of Gagan, and it's a very complex system. The ground segment itself is quite complicated with several ground stations, which are called the reference stations, distributed all over India. And the flight regime is called flight regime, India and around, and having land uplink stations, having a mission control center with very complicated, I would say, robust software system which can correct the errors, which can find the integrity of the system, and which can form the messages, and with a transmitting antenna, we can send the signals to the overlay satellites, which are geosatellites, INSAT class satellites, which in turn they send the signals down, which will be used by the aircrafts as well as the users. It is interesting to note that India became the first country in the Asia Pacific region to certify its system. Certification is a very elaborate process. It requires ICAO regulations and quite complex. For approach, only for the aircraft approach with vertical guidance. There is Cat 1, Cat 2, Cat 3, and so on. Significant steps for aviation safety. Okay, with Gagan, we wetted the hands in building a satellite navigation system, which is space-based. We had our own 3 satellites which were launched, We built the entire ground segment and then also the software included into it, and also how to work with such a system and how to certify the system. So with this experience, India started its own navigation system, space-based navigation system called IRNSS, Indian Regional Navigation Satellite System, or navigation with Indian constellation. It has got a small story. During Kargil War, which happened in 1998, at the intense moment when we were fighting at the borders, the Department of Defense or the US, supporting our neighbor, denied GPS to us. So we are not able to get GPS, and therefore what we depended upon for our own position determination, which was the GPS, was not available to us. And therefore we have to use indigenous means with difficulty to fight the war. But it's another story that Kargil war was a great success. So at that time, the Prime Minister, Atal Bihari Vajpayee, decided that we should not depend upon, the GPS system or any other international navigation system. We should have our own navigation system based on satellites. And we have the strength of the satellites. Therefore, he ordered ISRO to build our own navigational system and release the budget which is required for it. It is being implemented by ISRO. So IRNSS provides the user with targeted position accuracy of better than 20 meters. I think we get less than 10 meters. That was the mandate given over India and the region extending about 1,500 kilometers around India. See, to build a global navigation system like GPS, it requires billions of dollars. So with the limited money that was given to us, we can cover India and its neighborhood, 1,500 meters on all four sides, which is good enough for us to defend our country and to provide navigation to the countrymen and the people in the country. So, based on the mandate, we built a system. I have been one of the project directors for the ground segment. IRNSS, the mandate is to provide two signals. One is standard positioning service, an encrypted service provided to all users, to any civilian users, and a restricted service, an encrypted service provided only to authorized users. It has dual frequency. Navigation signals are transmitted in L5 and S-band frequencies. So here you see the navigation IRNS Navic constellation. The sales segment, as you can see in the diagram, comprises of 7 satellites, 3 sitting on the equator in geo orbit, and 4 to each on either side of the middle satellite. In geosynchronous orbit, which is inclined. Geosynchronous orbit has a time period as geo, 24 hours, but it's an inclined orbit, 11 degrees, going up and down. So these satellites are at 36,000 kilometers and cover the entire region of India and around. You can see an IRNS satellite on the right side of the slide, and the satellites use extremely accurate rubidium atomic clocks in each satellites. They are the heart of the system. It's open to all users, accuracy better than 10 meters. So the primary service region, as said earlier, is shown here. India's mainland and surrounding 1500 kilometers, where if at all we have to fight, we have the necessary navigation equipment, navigation system for us to defend our country. It's mainly for defense purpose. And an extended service where you get very accurate navigation information. That is 10 meters and less all the time, with 4 satellites available. And 4 satellites are really required in order to do a triangulation and time bias estimation, as it is required for a GPS satellite system. And extended service region as shown in the larger rectangle. Okay, this is about IRNSS and Gagan systems. The accuracy of IRNS system was, when it was completely built, was less than 10 meters. I have some slide which can show it is of the order of 2 meters. The time maintained at the timing center is accurate to less than 15 nanoseconds, and it feeds to the Indian Standard Time to NPL, and it is tied with the timekeepers of the world at Paris. NAVIC also is useful for fishermen safety, disaster management, smartphones, and so on. Then we'll talk about the deep space IDSN. IDSN is deep space navigation, deep space network facility. India's deep space network at Bailalu is India's listening post for the universe. You can say that. It houses 32-meter huge antenna, which is indigenous, built by ISTRAC and ECAL together for the first time, and 18-meter high gain antennas operating, and there is also 11-meter terminal tracking antenna operating in S-band, X-band, and Ka-band frequencies. These antennas can detect signals from millions of kilometers away. The range measurement accuracy is in centimeters, and velocity measurement accuracy is few millimeters per second, and they can track even beyond 2 million kilometers. DSN enables continuous communication and tracking for missions like Chandrayaan 1, 2, and 3, and Mangalyaan, Aditya L1, and the future Venus missions. It is fully integrated with ISTRAC Mission Control Center, where we can control the missions, space missions, any type of space mission, deep space mission, forming a real-time loop for telemetry, command, and control. IDSN also works with NASA DSN. NASA DSN has got 4 deep space networks, like the 64-meter antenna, and ESA's tracking stations, which are also 32 meters. This is an indigenously designed and built facility by ISRO and serves as India's lifeline to deep space. So we can take pride in this, and it's really capable. We can have, to describe this system, I encourage all of you to visit Bailalu and look at the grandeur of the system. 32-meter antenna. These are all the hardwares actually. First, we talked about navigation system, space-based navigation system built by ISRO, Gagan, and Navik. I can only outline, can't go into more details in a short time. But the navigation also involves enormous, extensive software because space missions involve trajectory and space satellites involve orbits. Trajectory and orbit determination software is a huge software system evolved over years in ISRO and operationally used for ISRO missions. They are not textbook ones or not just theoretical ones. They are operationally used for ISRO missions. All the data from the sensors, what we talked about, antennas, range rate systems, radars, and the DSN feed into a mammoth trajectory and orbit determination software, the brain of the navigation. These software systems are state-of-the-art, in-house developed, and validated systems, well calibrated with other systems like Goddard trajectory determination software. That's around the earlier stages and used in our real missions successfully. The orbit determination software continuously estimates where the spacecraft is and predicts where it will be. Combines mathematical models plus real-time sensor data. Uses two key schemes or methods. Some of you may be familiar with it. I'm just mentioning it. One is the differential correction method to define the state vector x, y, z, x dot, y dot, z dot, or orbital elements a, e, I, omega, capital omega, and nu. Iteratively in a batch processing mode, that is what is differential correction. Or in a Kalman filtering process to merge real-time tracking sensor data while filtering the noise and other errors and estimating the state vector or the orbital elements in real time. The software integrates the data from radar altimeter, star sensors, INS, and is further enhanced by laser tracking data. Achieves meter level accuracy in orbit, Earth orbit, tens of meters in deep space. So, needless to say, this software, put only in one slide, work of several years, is the brain of navigation. I had the opportunity to work in the orbit determination software. Mathematical modeling is behind every trajectory. Behind every trajectory lies mathematics. Complex modeling and numerical integration. ISRO's navigation models include multiple gravitational influence of Earth, Moon, Sun, other planets. Perturbations like Earth's oblateness. Earth is not a sphere, it's an oblate spheroid, which is described by a legendre polynomial of nth order. Atmospheric drag, solar radiation pressure, tidal effects, and so on. These nonlinear equations of state, differential equations, integrated, solved numerically using Rangikuta methods, which you might have studied, prediction correction methods, such as Adam Bashforth and Adam Moulton schemes, both higher order and adaptive methods, Gauss-Jackson method, that ensures long-term stability. Adaptive step size for stability during long maneuvers. During missions, thousands of sensors, thousands, even millions of sensors, thousands of sensor readings per second are fused together through Kalman filters, providing continuous correction. The accuracy is achieved using this software, adopting the mathematical modeling which we have done over years, which we have really sophisticated over years. For INSAT satellites, we are able to get less than 100 meters at 36,000 kilometers. 100 meters is good enough for INSAT satellites. And there are different software systems for different missions. For orbit error and for attitude pointing, we have attitude determination software, which can determine the attitude to the accuracy of 0.05 arcsecond. IRS missions require, because they are looking at the ground, taking images, require less than 10 meters, of the order of 1 or 2 meters. So orbit error, orbit determination software, and prediction software can give this much of error. And the pointing accuracy realized is 0.01 arcsecond. Chandrayaan 1, to give you an idea, is plus minus 50 meter orbit, 5 millimeters per second in velocity error. Chandrayaan 3, which had to land precisely at a point earmarked for that purpose near the South Pole, had an error ellipse of less than 400 meters. Within 400 meters, it landed. Mangalyaan trajectory error is less than 2 kilometers after 650 million kilometers, not 650 kilometers, 650 million kilometers. There is a small typing error there. So this is a capability that we have achieved over 3 or 4 decades of struggling and finalizing, working, experimenting, and then really realizing the potential software system along with the hardware system for navigation. Now, let's quickly go through navigation in Indian interplanetary missions. So we'll consider navigation in Chandrayaan mission first. So let us now move from Earth to Moon, which is around 400,000 kilometers, 384,000 kilometers. But mean value is 400,000 kilometers away from us. Chandrayaan 1, I will not go through the entire text, you know this, mapped. It's a path-breaking mission for India. It was launched in 2008. It proved the ability to perform orbital and deep space operations to map Moon, which was achieved through robust ground-based tracking and command systems, including the IDSN. Chandrayaan's navigation was primarily about establishing a stable orbit and maintaining communication, necessary foundational capability for future missions. But it was a great success story for India. Chandrayaan 2 is a mission which is a forerunner for Chandrayaan 3. And throughout the Earth to Moon and the lunar orbit phases, ISRO's IDSN tracked and monitored the spacecraft position and velocity. It had an orbiter, a lander, and a rover. The orbiter used star tracker to help determine its orientation and maintain its precise 100 kilometers by 100 kilometer polar orbit around the Moon. For the autonomous landing sequence, Vikram relied on its orbital onboard navigation guidance and control system. Inertial navigation system, INS package, track the lander's changes in position and velocity using accelerometers and gyros. To correct for INS drift errors, several absolute sensors were used to measure the lander's state and relative to lunar surface. Unfortunately, the lander crashed. The orbiter succeeded beautifully, but the lander crashed due to velocity misestimation, navigation error. So, correcting all those errors, we went for Chandrayaan 3 mission in 2023, which was a great, grand success. Chandrayaan 3 is a navigation excellence, launched by a small launch vehicle, unlike, other European and not Europeans have not launched, the Chinese and, let's say, NASA. Launched by our PSLV launch vehicle. Terrain relative navigation with us. And the most important thing is, all the rest of things we have proved with Chandrayaan 2. Now the landing as well as the function of the rover collecting data was proved exemplary in an exemplary manner by Chandrayaan 3. So the terrain means moon terrain, relative navigation is done with laser altimeter, hazard detection cameras, autonomous detection making or special features. Trajectory and navigation involved so many things, which I'll show in one of the next slides. I'll say now. It involved orbit raising around the Earth, translunar injection, lunar capture. You can see the mission actually. Orbit raising around the Earth, because PSLV cannot put the Chandrayaan 3 directly into the moon's orbit. So we have to do a trick of maneuvering the spacecraft around the Earth, increasing the size of the ellipse around the Earth and increasing it so large that it goes very near to the moon. So it is called orbit raising around the Earth. Then comes when it is going in a larger ellipse, which takes it closer to the moon, still under the influence of gravity. It has to get into the gravity of the moon now in order to become an object of moon, lunar mission. Therefore, it has to be done at a particular point, which is called lunar orbit insertion point, where you have to give at a precise time a particular velocity so that the spacecraft gets locked onto the gravity of the moon. So that's what has been done. It's a very, very tricky maneuver. And we have done it very correctly. Yeah, we have done it in Chandrayaan 1 and Chandrayaan 2 and Chandrayaan 3 as well. So that is called lunar capture. Then once you are into the lunar orbit, you have to deorbit, rough and fine braking. And once you have done the final orbiting trajectory, final lunar orbit, then the lander has to get separated from the propulsion module and then land exactly at the point where it was intended to land, near the south pole. And terminal descent with rough and fine braking by lander is a real great achievement. The key, precise step-by-step navigation. Just knew this. But the PSLV satellite is taking. These are the events in the launch vehicle trajectory. Stages will get separated. Airports got separated now. HCL got separated. You can see it got separated. Aerodynamic engine was shut off. Now, the projection module along with the satellite is on the way on its mission to the moon. So as I explained earlier, that raise the orbit around the Earth, but we don't have enough energy. Propulsion PSLV doesn't have that much of energy. So it is directly into the Earth. Now, you may say, yeah, I think you are able to listen. So around 16:30, we have reached the intersection point, and satellite has gotten into lunar orbit. So the second and final deboosting happens. The animation is self-explanatory. And the descent, the last 15 minutes, which are very critical. You have to descend at less than 0.1 meter per second, so that there is soft landing. After a soft landing, the rover comes out. And so, precise step-by-step navigation marked the accuracy of our navigation systems and our mastery, both in hardware, software, and mission planning, analysis, and operations for this mission. It's a great success story. Hello, I think you are able to listen to me.
Yes, sir. Yes, sir.
Yeah. Next comes another major mission, Mangalyaan as it is called, colloquially called Mars Orbiter Mission, MOM, M-O-M, MOM, Mummy, is one of the greatest space navigation stories in the history. One of the main objectives of MOM was to develop technologies required for design, planning, management, and operation of interplanetary mission. This was done in 2014. It has a lot of fuss actually. India is the first Asian country to become successfully send mission to Mars. Fourth in the world, next only to USA, USSR, and ESA. In a record time of 18 months, compared to NASA's 5 years for its first mission, Maven. Very cost effective, with a budget of 73 millions, about 450 crores. It's very less money actually. It was one of the most economical Mars missions. First attempt success, India holds the record for successfully capturing the Martian orbit on its first attempt, an achievement unparalleled globally. India's mission costs significantly less than Maven mission, which is $671, 73 versus 671 GC, 10 times almost, 9 times. The IDSN performed very accurate tracking and navigation to ensure the spacecraft remained on its correct trajectory over the vast interplanetary distance. For the initial phases of the mission, the IDSN used smaller 18-meter antenna. Once Mangalyaan was farther away, the more powerful 32-meter dish antenna was brought into service for deep space communication and navigation. So these visuals, diagrams explain the orbit raising strategy. PSLV, as in Chandrayaan, could not send the, Mangalyaan directly to Mars. So ISRO raised its orbit in stages, as was done in Chandrayaan, around the Earth. And, from Earth gravity, the Mars orbiter, gets into the Sun gravity and moves in its elliptical orbit. So precisely calculated so that almost after off the ellipse, it goes closer to the Mars. So like we inserted Chandrayaan into lunar trajectory, lunar gravity, there Mars insertion, trans-Mars injection, a single critical burn, it to sent it to heliocentric orbit, and the journey to Mars in the trans-Mars injection orbit, heliocentric sun-centered orbit, is around 300 days. You have to keep tracking it and then monitoring the satellite, keeping the health in perfect order. And after 300 days, it reaches 650 million kilometers away from the Earth and close to Mars. And Mars orbit insertion, a perfectly timed burn. Burn means burning the thrusters, rocket. Slowed the spacecraft into Mars orbit. So it was going in hyperbolic orbit with very high speed at a particular point, which is called the Mars insertion point. One has to burn the, thrusters exactly at that time to reduce the velocity so that it gets into the Mars orbit. India became the first nation to reach Mars on its first attempt. So this is what it is. You can see the PSLV launch vehicle, a small vehicle, but still took us to Mars. And Mars orbiter satellite, which is quite complex and complicated, with its propulsion system, which is the heart of the system, and also the navigation system, which forms the backbone along with the control and guidance system, which is autonomous. So these missions really showcase our capability in space navigation, which is followed by several other missions subsequently. The mission to Sun, the Lagrangian point, L1, from where you will be able to observe the Sun all the time, was also a wonder in space navigation. We are able to keep the satellite, it's called Aditya L1 mission. Satellite at a point around the Lagrangian point, which is a balancing point between the Earth and the Sun, system. And you have to, the satellite moves in a halo orbit, and you have to keep it very precisely in that orbit. If you allow it to go, it will run away. And that requires continuous monitoring, continuous position and velocity determination, orbit determination, orbit prediction, and performing the maneuvers, pre-maneuver, post-maneuver, navigation systems. And all this showed our power, technological power in the area of space navigation. So we have Chandrayaan 4 coming up and Mangalyaan 2 coming up. And so the next coming up mission is the mission to Venus, which is an interior planet. All these are lined up. And of course, the experience, the expertise that we have gained in Chandrayaan and Mangalyaan and Aditya L1 missions will easily take us through in all this mission. Several thousands of people worked day and night in order to achieve this kind of precision and accuracy. So we are coming almost close to the presentation. So in the part 4, we'll see the challenges, future directions, and a few conclusions, if we can talk about that. There are a lot of challenges, of course, in the area of space navigation. Limited space tracking infrastructure. See, we have only one IDSN station, whereas ESA and NASA, NASA has four not IDSN, DSN stations distributed around the globe so that it can track the space mission continuously. So we have to sometimes take support from this NASA and ESA, European Space Agency infrastructure. So limited deep space tracking infrastructure is a challenge. So we have to build some more. We have to build our deep space network in foreign countries. It's a real challenge. Friendly countries, of course. Communication delays more than 20 minutes to Mars, for example, we have said 650 million kilometers, entails autonomous control. Precision landing, Chandrayaan 4, for example, demands meter level accuracy. These are the challenges. Software complexity. Testing this software is months and months of work by several engineers, validating them and then proving them in the actual missions. Computational loads with a mission scope increases actually. Added to that, we have the budgetary constraints. Budget becomes an issue. Of course, nowadays, budget is not a major issue for ISRO because Prime Minister, who is heading the Space Department, understands the importance of space and talks about the space programs of India and our leadership in space programs everywhere, wherever he goes, and takes pride in that. And therefore, he also gives enough budget that is required for some of our missions. I can say in simple terms, space navigation pushes the limits of mathematics, hardware, software, and budget. India has kept pace through ingenuity, our own engineered methods. I just touch upon the future navigation concepts and technologies. Lunar GNSS. GNSS means Global Navigation Satellite System. IRNSS is a regional navigation system. It will be upgraded into a global navigation system with our future equivalent GPS or GLONASS or BeiDou systems, which requires enormous amount of money, time, and effort. Lunar GNSS is a network of satellites around the moon to guide astronauts and rovers, because mission to moon is a dictum of USA, Europe, and China. We also have that mission. So a network of satellites around the moon to guide astronauts and rovers, forms the lunar GNSS system, is being built. We will also be a partner to it. Pulsar navigation is an advanced idea. Pulsars emit extremely regular pulses. They are nature's atomic clocks. Spacecrafts can triangulate position independently with pulsars. Is evolving in the experimental phase. A vehicle using XNAV would compare received X-ray signals with a database of unknown pulses, frequencies, and locations and navigate itself. And of course, needless to say that it is the AI world now. AI is going to revolutionize the navigation, revolutionize decision-making systems. And AI navigation and autonomy includes spacecraft making autonomous decisions. And Chandrayaan 3 certainly had some features of this kind, is an early example. AI enhances space navigation by enabling autonomous decision making, terrain analysis, and real-time trajectory adjustments, especially vital for deep space missions and planetary exploration. So before I conclude, India now has Navik for Earth, Chandrayaan for lunar navigation, Mangalyaan for Mars, Aditya L1 for solar observation, IDSM for deep space navigation. A full navigation ecosystem. India has mastered Earth, Moon, Mars, and Sun navigation. We are planning to reach Venus. When a nation learns to navigate space, it learns to navigate its own future. Okay, to conclude, India's journey in space navigation, which reflects vision, resilience, and scientific brilliance. From modest Earth orbit satellites to complex interplanetary missions, ISRO built complete self-reliance in trajectory design, timing systems, software modeling, and sensor integration. I am reiterating. Navigation remains one of the backbones of CNG, command, navigation, and guidance. Every successful orbit, maneuver, and landing owes its success to precise navigation. With atomic clocks, deep space tracking, and AI-based models, India is well positioned to conquer not just space, but future itself. That's what I said in the last slide as well. So, India's journey in space is a navigation dreams to reality. Navigation of dreams to reality. Thank you. Within the short time, I quickly covered many things. And each one of the aspects I talked about would require several hours of presentation. This is what I could do for ATAL program. I thank you for your listening.
That was a fantastic presentation. Thank you so much, Professor Soma, for delivering such an insightful and thought-provoking session. Your vast experience with ISRO, your clarity in presenting complex navigation concepts, and your inspiring real-world perspectives on NAVIC and satellite applications have truly enriched our understanding. We are grateful for your time, your wisdom, and your willingness to share decades of knowledge with all of us. On behalf of AACT Atal Academy, our institution, the organizing committee, and all the participants, we extend our sincere and wholehearted appreciation to you, sir. Thank you so much once again. Organizers, can we have any queries? Anything to be clarified with, sir?
or you can send queries to my email som598 som, all small letters, 598 at yahoo.com. I'll be too glad to answer.
That was a fantastic idea. Thank you so much once again, sir. Thank you.
Thank you for the opportunity. I enjoyed this 1.5 hours.
Thank you, sir. Thank you very much for your valuable lecture, sir.
Thank you, Mukesh, for giving me this
Thank you, sir. Thank you, sir.
opportunity.
Thank you, sir.
Dr. Mukesh, sir.
Sir,
Shall
the next
section?
session will start by another 5 to 10 minutes, sir. So I informed the next resource person, sir. He will join because with respect to the schedule, it is scheduled by 8 p.m. So
Exactly.
we have to wait for another 5 minutes. Please inform the participants to wait for another 5 minutes, sir.
So I hope everyone would have heard this information. Maybe in a couple of minutes, next resource person may join. So kindly wait.
Hello, sir. For feedback forms, it will be for individual sessions or for a day? Feedback form, sir.
Sir, for individual sessions, it will be sent, sir, through WhatsApp as well as in the chat also, we will post it.
Okay, thank you.
I log out, Mukesh.
Yes, sir, please, sir. Thank you, sir. Thank you very much, sir.
We are so much grateful to you, sir. Thank you.
I'm leaving the meeting. I am extremely thankful to the management, ATAL Faculty Development Program, for the opportunity that is given for me to share some of the projects in which I have worked and share my knowledge and speak about my organization, Indian Space Research Organization, and its contribution to Indian space. Thank you. God bless everyone.
Thank you, sir. The Google form has been posted in the WhatsApp group. Kindly fill. Everyone, please fill the form for this session. And the next session will be within another 5 minutes. The resource person will be joined. So he will start the session within the next 5 minutes. Good evening, sir. I welcome Dr. Ashish K. Shukla, sir. Now I request Madam to give the introduction about the resource person.
Am I audible, Dr. Mukesh?
Yes, sir. Yes, sir. You are audible, sir.
Okay.
1 minute, sir.
Yeah,
Our
sure.
professor will give you an introduction about you, sir.
Sure.
Next session. I now request one of our beloved professors, Dr. Ashish K. Shukla, who is the expert for the next session. Please, madam.
Good evening to everyone. It's my privilege to introduce our esteemed speaker for today's session, Dr. Ashish Kumar Shukla, a distinguished scientist and a leading expert in the field of satellite navigation in India. Dr. Shukla completed his PhD in applied fluid mechanics from Lucknow University in 2003. He joined the Space Application Center, ISRO, Ahmedabad in 2005 and currently serves as scientist and head of the Advanced Navigation and Science Applications Division. With nearly 2 decades of dedicated work in satellite navigation, he has played a pivotal role in shaping India's navigation ecosystem. Dr. Shukla has significantly contributed to two of India's most prestigious navigation programs, GAGAN and IRNSS, NAVIC, right from their inception. He was also a key member of the team that successfully developed the GPS and NAVIC user receiver, enabling indigenous navigation capability for strategic and civilian applications. He currently serves as Deputy Project Director of the RLV pseudo-light system, where he led the team responsible for 3 consecutive successful landings of reusable launch vehicle using lateral guidance from the pseudo-light system, an achievement of the national pride. One of his visionary contributions includes conceptualizing and proposing pseudolite based navigation for lunar missions, laying the foundation for lunar positioning, navigation, and timing. His expertise has been recognized globally, and he has represented India as co chair in the International Committee on GNSS and in multilateral workshops on cislunar PNT under the United Nations Office for Outer Space Affairs. Dr. Shukla's research extends to cutting edge domains, including machine learning based GNSS multipath classification, LSTM driven ionospheric modeling, GNSS reflectometry, underwater navigation, and alternate PNT architectures using low Earth orbit satellites and pseudolights. For his outstanding contributions, he has been honored with the ISRO Team Excellence Award and the National Geomatics Award for Technology, and he has authored more than 75 peer-reviewed publications. We are truly honored to have with us today a visionary scientist and a driving force behind India's emerging leadership in global navigation technologies. Ladies and gentlemen, please join me in welcoming Dr. Ashish Kumar Shukla to deliver his expert lecture on overview of SATNAV applications. Please, sir.
Yeah, thank you, madam, for your kind words. And uh, it is truly a pleasure to talk about navigation applications here on this platform. So I'm very thankful to Dr. Mukesh as well, who approached me to deliver this talk. So I start it. Hope I'm audible. And how much time I'm having? I will have to stop at 9:15, I think.
Sir, 9 to 9:15, sir.
Okay. So I will try to cover within an hour, and if you have some question, we will discuss in the after the presentation. So, let me talk about overview of ISRO SATNAV applications. So the outline of presentation is as follows. First, I will cover GNSS system. GNSS calls for Global Navigation Satellite System. So the overview of the GNSS, including our NAVIC. As we know, India is developing NAVIC system. Then I will come to GNSS measurements, which are done by the GNSS receivers. Why I'm coming to the measurements? Because a lot of applications are driven by the different kind of measurements from the receivers, like pseudo range, carrier range, Doppler, etc. So I will cover very briefly about them. Then I will talk about what are the error sources when we estimate position between satellite and receiver using signal processing knowledge and their mitigations. Then application with precise point techniques, positioning techniques such as differential positioning and real-time kinematic positioning, which we call as in short as RTK. Then precise point positioning, I will give some glimpse of that PPP. Then GNSS applications related to AI, ML, and deep learning models. We have successfully applied these kind of models in some of the uh, newer application, you can say, like multipath, ionosphere study, and some of applications are underway. Then navigation for aviation application. Here I will cover reusable launch vehicle system, where we have provided lateral guidance using newly developed pseudolite system for aviation application in Space Application Center, Ahmedabad. So this was done very first time in India. So then right now new domain has arisen, which is called LEO PNT. The advantage are that it is very it is sending very high power signals to the receiver due to its proximity of LEO orbit to the Earth. So they are difficult to jam and they are moving faster also. So if some jammer tries, it will be difficult again. And then in the last, I will cover lunar PNT and interplanetary navigation. So this slide is changing. Is it visible?
Yes, sir. Slide is changing, sir.
Okay, okay, thank you. So this is how we see a global navigation satellite system. It has majorly three segments. One we call as a space segment. Here on the right side, you can see there are satellites in a space segment. So this is constituted by satellite constellations, which may be global in nature or regional in nature. As you might be knowing, GPS, Galileo, GLONASS, BEDO, these are global navigation satellite system. If you have a receiver in your hand or in your mobile or any scientific receiver, and if you place at any place of the earth, you can find out your location. So this is the job of global positioning system. Then regional systems are there, which cover lesser part of the globe, like Navik covers Indian territory plus 1500-kilometer boundary. So these systems are meant for covering India and some other places of strategic importance. Then control segment, we call it ground segment also. So in ground, a lot of infrastructure is required, which is responsible for generating some additional corrections of orbit and clock and ionosphere. These are very important. These corrections are generated with the help of the ground infrastructure of dual frequency receivers, as you can see in the picture, right corner. And they generate this correction, and these corrections are uplinked through the very big uplink antennas near by Lalu. After getting these corrections, satellite reformats these corrections and again transmits to the user as part of navigation data or navigation signals. Then, as you know, ionosphere is a very turbulent in Indian region. Reason is that India lies in equatorial ionospheric anomaly region. So corrections are required very frequently. Like GPS relies on Klobuchar model of ionosphere, but that model doesn't work well in Indian region. So some INO corrections data is generated and uplinked. Then in user segment, you can see there are a lot of users in leftmost circle, you can see, or ellipse. So here you can see user may be traveling by some car, in an aeroplane, or on fighter jet, or resting in some resort or in marine environment. So or even people blind people which get support from GNSS system nowadays, and a lot of other users are there. So these are the three basic segments: space segment, control segment or ground segment, and user segment. Space segment contains satellites. Control segment is responsible for generating accurate navigation data and uplinking to the satellite. And user segment consists of receivers, which are we call generally as GNSS receiver or GNSS chips, which we are having in our mobiles. So now there is a question often asked when GPS, Galileo, GLONASS, BEDO, all those global systems are there. Why India is developing its own navigation system, NAVIC? So answer is you might be knowing during 2000 time frame there was Kargil war and with the neighbor country and uh, that time India wanted some locations through GPS from US and that due to some political reasons they were denied. So that was the stepping stone, or you can say triggering factor that India thought to become self-dependent in position, navigation, and timing capability. So the starting of NAVIC was due to this fact, which triggered the development of NAVIC. NAVIC is meant for navigation with Indian constellation. So so now uh, uh, as you see, necessity is the mother of invention. So we have this system now in place, and we are doing this positioning using our NAVIC as well. One more thing I will like to add here. Nowadays, it's a time of multi-constellation receiver or receiver chips. So, nobody alone uses GPS right now, alone Navic right now, or alone Galileo right now. They make a chip and it can process all the signal together. So that's a great thing. And but Navic is also part of this multi-constellation chips or receivers right now. So that's a big thing for India. And ISRO, uh, it was developed fully in ISRO and from satellites to ground segments to the user segments. So right now industry is developing user receivers which we will be using in future. So Navik, as you know, it's a regional constellation. So it is a combination of geostationary Earth orbit (GEO) satellites and GSO geostationary geosynchronous orbit satellites. So there are 3 GEO satellites and 4 GSO satellites in legacy GNSS legacy Navik system, and it provides accurate position, velocity, and time to the user with position better than 20 meter 3 sigma accuracy and timing with 20 nanosecond accuracy. And as I have told, it covers Indian landmass and 1500 kilometer beyond the geopolitical boundary. It's a all-weather system, and it provides accuracy at par with the GPS because it has more accurate grid-based INO correction model. So now coming to the measurements, as I have told in the outline slide, the applications are majorly driven by the different kind of measurements GNSS receiver can measure and process. So here on the left side, I have shown you two scales. Upper scale is uh, 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 equivalent to generating pseudo range measurements. So, and lower scale is carrier responsible for generating carrier range measurements. So, as you have seen screw gauge and vernier calipers in your lower classes, here on the same analogy, we can see upper scale is having cursor marks. So any receiver, so this is a one chip mark of a ranging code. There are ranging codes transmitted from the satellite. So one chip is around 300 meter length. So receiver can measure or generate the measurements with 1% of this code chip, so which comes out to be 3 meter. However, lower scale, you see that markers are very finer markers are there in comparison to upper scale, if you see. So these are the carrier cycles. At L1 GPS L1 frequency, one carrier cycle is 19 centimeter. On L2 it is 24 centimeter, and on S band it is 12 centimeter. So these markers are derived by the length of the or wavelength, we can say, which I have just told. So receiver can measure 1% of this wavelength. So 1% of, you can imagine, 19 or 20 centimeter comes out to be sub-millimeter level. So the measurements generated by pseudo range are less accurate, but they are very stable. And measurements generated by carrier range, which is shown in lower scale, are very accurate, but they are very fragile. If something happens due to atmospheric scintillation or some other phenomena, there is a rapid power fluctuations. So these carrier range measurements will not be available because they are generated by phased lock loop PLL, and PLL is most vulnerable and it gets unlocked. However, you can see on the right part in the graph that from pseudo range we can have, which is shown in the blue part. This graph is generated by our own data from SATNAV, and we can see the variations are more than 5 meter level. They are due to multipath or incapability to resolve to the finer level in comparison to carrier range. And this red line, which is going almost through the center of or average line of this blue one measurements. So you can see this is very precise and accurate. So using the measurements, this is from carrier range or carrier cycles. So they are very accurate because they have less multipath, and pseudo range is having more multipath and resolution is more coarser than carrier range. So you can appreciate that using carrier range we can get centimeter to millimeter level accuracy. However, using pseudo range we can go up to meter level accuracy only. So these measurements are responsible for various kind of applications, such as if you go for geodesy or survey purpose, you must be having a receiver which can provide you centimeter to millimeter level accuracy. Suppose you want to survey a field or farm where you do agriculture and other people's fields are also there. So if they are uh, accurate in centimeter or millimeter level, the farmers will be more happy to get the survey done. And if it is in meter level accuracy, then there will be disputes that somebody's field may be measured in some other's portion. So that kind of things are there. And if you are a user in the car navigating with using GNSS receiver kind of guidance, then you don't require millimeter level accuracy. There you can have sub-meter or meter level accuracy, that's enough. So this is the mathematical equation of pseudo range and carrier range. In pseudo range, you can see it is the summation of true range plus receiver clock bias, satellite clock bias, ionospheric delay, tropospheric delay, and the portion in blue is multipath and other smaller errors. In carrier range, there is a true range, then satellite clock bias, receiver clock bias, ionospheric delay, tropospheric delay, and one term integer ambiguity lambda n comes. And blue part is multipath plus other noise. Here, why I have highlighted blue part, that this is majorly the content from multipath. So multipath error is very high, as I have shown in the graph in previous slide. in pseudo range, whereas in carrier range, multipath is in millimeter level. So we can be, so this carrier range can give you more accurate measurements. However, there is integer ambiguity part and there are cycle slips in carrier range. As I have told, there are power fluctuations in this measurement. So though they are very accurate, but they are difficult to handle and very advanced level algorithms are required to handle them. So there is a price tag. However, pseudo range doesn't require any such kind of thing. However, it is its accuracy is in meter level. So now coming to the mitigation of errors. So before that, we must have the knowledge of sources of error in GNSS measurements or whatever way we measure the distance from satellite to the receiver. It's, for calculating the position, we require two things: distance between satellite to the receiver and the coordinate of the satellite themselves. So if we have these two things and we can remove the errors, we can have accurate position. So error sources are categorized in these things, which are satellite clock error, satellite orbit error, ionospheric delay, tropospheric delay, receiver noise, and multipath. So as I have shown you in the uh, 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 equation in previous slide, this satellite clock error, these are the residual errors rather on second column. So it is plus minus 2 meter level. Orbit error is 2.5 meter. INO delay for single frequency may go up to 5 meter. Tropospheric delay is half meter. Receiver noise 30 centimeter. And multipath varies within plus minus 1 meter accuracy. So these are the residual errors. If we correct all left hand side first column things to the best of our knowledge, these are the residual errors in second column which are still left. These are the worst cases. Error generally are within this range, so it may be 1 meter, sometimes 1.5 or 0.5 meter, but worst case it is 2 meters satellite clock error. Likewise other errors. So we want to, if we have some control on this errors, we can have better accuracies in centimeter to millimeter level using carrier range measurements. And if we have this kind of error is still there with pseudo range measurements, this constitutes the overall error budget in the range, and it comes out to be somewhere 3 to 4 meter or 5 meter level, because these are independent errors. So to get the estimate of this error, we have to square all the errors and sum it and then take the square root. So that constitutes our total error budget in the range measurement. Another factor is position accuracy is a combination of range error into geometry of the satellites, where satellites are spread in the space. So if a spread is less, there is a position dilution of precision factor which is derived by the geometry. So we call it PDOP. So if a spread is less, PDOP will be more. It's a direct multiplier in the range errors. So any question?
Nothing, sir. Nothing, sir. Please proceed.
Okay. So these PDOP has to be minimized. So ideally it is 1 or below 1, but it is not achieved in general. So we when we design the system, we put a lot of attention how the satellites would be spread in the space. Spread should be more, so volume made at the receiver from the satellite would be more, and this volume is inversely proportional to PDOP. So PDOP we want as less as possible, because it is multiplied with range error which are somewhere 3 to 5 meter level. And if PDOP is 1, our position accuracy is 3 meter. If PDOP is 2, 3 into 2, it will be 6 meter likewise. So let us see how we handle this. So one slide is on propagation delay experienced by GNSS signal. So there are ionosphere and troposphere, through which ionosphere is a dispersive medium, means every frequency when travels through the ionosphere, travels through slightly different paths, and when it comes out from the ionosphere, there is a slight delay in nanosecond level. This is a pictorial view only. It doesn't happen the way it is shown, but just for your understanding, we have L1 and L2 signals. So you can see this yellow patch is ionosphere. So if signal is passing through the ionosphere, it is taking different paths and coming to the receiver, which is shown on the Earth surface. So if we have two frequencies, only ionosphere is dispersive medium. It responds differently to different frequencies. So if we have two frequency transmitted signal and received at the receiver, receiver will measure the ranges from L1 and L2, and if we subtract these ranges, then what we are left with, ionospheric delay, which is measured in terms of total electron content, which is nothing but if we draw an imaginary cylinder from receiver to satellite, number of electrons per meter square area is called total electron content. So we measure ionospheric delay in terms of TC. We call it TEC. So likewise, there is a troposphere. Phenomena is different from ionosphere and troposphere. In troposphere, there are wet and dry delay. Wet delay is due to the water vapor or moisture present. It is varying locally at different places. However, the wet delay is 10% only, and major delay, tropospheric delay, 90% is from dry gases of from the molecules of nitrogen and oxygen. So there are very precise models of troposphere. We can use them and mitigate this error up to millimeter or centimeter level accuracy. So now coming to positioning techniques for error mitigation. So we use code and carrier phase measurements, which I have just described. So there is a concept of differential NAVIC or differential GNSS. In that, I will explain in coming slides. So we do code phase based differential and carrier phase based differential. Code phase based differential positioning can give us sub-meter level accuracy. This is used in our Gagan system, which is called uh, wide area augmentation system. Or we call it as satellite based augmentation system, SBAS. Then carrier phase based, these measurements are not used by SBAS system, because SBAS system is a safety of life service. There are passengers in aircraft. To them, this service is being provided. So carrier phase measurements are very vulnerable, as I have told. They can get, receiver can get unlocked. So these measurements are not preferred option for safety of life operations. But we can do survey and many other things using carrier phase measurements, and we can get the centimeter to meter level accuracy. Then there is a technique called precise point positioning, PPP. So it is done using a single receiver. Then here we require additional orbit and clock products. I will throw some light in subsequent slides. So they require dual frequency receivers, essentially carrier phase measurements and orbit and clock products additionally. So using that, we can have 10 centimeter level accuracy. So a lot of companies are providing those services in a lot of commercial receivers right now. So this is what we can achieve from any GNSS system. It's a very very nice slide. It is taken from Parkinson's book, who was one of the founders of GPS. So you can see on x-axis position error is shown, and y-axis there are two variants: autonomous position and differential position. And on the upper side you can see carrier phase measurements and code phase measurements. So if I take code phase measurements, which are shown in blue, then differential positioning, which is used in Gagan and SBAS kind of services, it gives best position accuracy of some 1 meter or like that. However, if we take carrier phase measurements and whether we operate it in autonomous or differential mode, our accuracy may range from some 10 centimeter to 1 millimeter level. So that is what we can achieve from the any GNSS system in various modes with various kind of receiver measurements. So now coming to, I've used the word differential GPS or differential NAVIC. So let us see what is that. In that, there we need essentially two receivers. One receiver is called base station or reference station. Other is called rover. Rover doesn't know its position, but base knows its position from the survey or any other method. So that exact position is inserted into the receiver and it becomes the base station. Now here in differential positioning condition is base and rover should see the same set of satellites as you can see in the right hand side. Both the receivers are seeing same set of satellites and getting the signals from them and doing the sorry carrier phase or pseudo range measurements. Then base station knows its location, so it can estimate its true distance from satellite to receiver because satellite location is known and receiver location is also very perfectly known. So we get a true estimate of the range between satellite and receiver. Now receiver is also measuring pseudo range, which is corrupted by satellite clock error, orbit error, ionosphere, troposphere, multipath, and so on. So it measures a range which is not as correct as the true range, okay, which we know when we know the location of the reference station or base station. So the difference of this true range and range estimated by the receiver is called the correction term. This correction term is supplied from base to the rover over 50 to 100 kilometer distance. Since rover is seeing the same set of satellites, so this correction is valid at the rover location as well. So rover applies this correction in all its measurements and it can mitigate all the errors which I have shown you in the table, 2 meter, 2.5 meter, 5 meter, or and so on. So these errors are now reduced to the centimeter to millimeter level. That's how differential positioning can give you centimeter to millimeter level position accuracy. So here it is shown in this picture how it is done. In the left side, you can see there are two receivers, one satellite. So errors common to the satellites are cancelled out when we difference two measurements. So we call it as single difference. Then there are two receivers and two satellites. So we take one more difference using another satellite. So here all the possible errors in pseudo range are cancelled out and we get very clean measurements, though they are different measurements, but using some different kind of algorithm we can process these different measurements and we can get centimeter to millimeter level accuracy. Now coming to major GNSS or NAVIC application, there are so many applications. You name anything, uh, 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 any anything in your life, you can see they are covered by GNSS uh, application. Like some of them are listed here: civil aviation, like automatic landing of aircraft for which Gagan was born. Then survey and land record, fleet monitoring, tracking, maritime navigation, railways, strategic, remote sensing, science application like TC, and many other things. People do some very new kind of application right now, like lightning detection using GNSS signal. So what are the possibilities? Then GNSS reflectometry, weather monitoring and prediction, location-based services, mobile phone-based consumer services, tourism, disaster management, and so on. So I can't list all the applications. So you see, when I will tell you in subsequent slides some of application, you will appreciate that how GNSS has made difference in your life. So now coming to the differential positioning I have covered. Now coming to the precise point positioning. Why I am covering? Because they address different class of applications in our life. As I have told, some require very accurate positioning, some require coarser positioning, like person traveling in car. So PPPs, I will come to this slide first. Difference between normal positioning and precise point positioning is that in normal positioning, we have broadcast orbit and clock errors. As I have told in my first slide that in ground segment there are they generate orbit, clock, and INO corrections. Okay, so this orbit and clock corrections are constitute around 4 to 5 meter error budget, worst case. Then they use pseudo range and meter level accuracy is there. But in precise point positioning, this 4 to 5 meter error which is coming from orbit and clock only, that reduces to centimeter level using additional precise orbit and clock products which are generated using additional ground infrastructure of dual frequency receiver. So it is costly, but it is a global service giving 10 centimeter level accuracy. Here we essentially use carrier range along with pseudo range, and we use dual frequency receivers. So using additional orbit and clock products using a single receiver, we can give 10 centimeter level accuracy, which is called precise point positioning. Now advantage of and disadvantage of precise point positioning are it is economical. As you see, only one receiver is required. In differential positioning, to come down to centimeter level accuracy, minimum 2 receivers are required. And so this is convenient also, reliable also, and it is not limited by baseline length. In differential positioning, where two base and rover receivers are, distance between them is called baseline. So accuracy depends on baseline. However, PPP is a global service. It gives 10 centimeter accuracy throughout. And so, but what is the major disadvantage? There is a convergence time. It takes a lot of time to converge down to 10 centimeter level. It takes around 30 to 45 minutes sometimes. But now, as I've told, it's an era of multi-constellation receiver. So we have a lot of signals available. So using processing all the signals together, some Trimble and other company receivers, they are claiming that they have brought down this convergence time up to some tenths of second level, or at least in minute level. So it's a great uh, R&D being done by the receiver manufacturers. So PPP is very useful now in people's life. Farmers are using in precision agriculture and many other applications. So this is the summary of position accuracy of a standalone versus differential GNSS and PPP. So you can see on x-axis again there is a baseline, 10 kilometer, 100 kilometer, 1000 kilometer to 10,000 kilometer. Baseline is distance between base station and rover. Okay, and y-axis shows the accuracy achieved from 1 centimeter to 10 meter level range. So you can see GNSS standalone give you 10 meter accuracy over any baseline. Then S-bus and differential GNSS can give you somewhere, 20 or 30 centimeter to 1 meter or 1.5 meter level accuracy. Then these are differential positioning techniques. RTK, real-time kinematic. Here you see they cover wide range of baseline, wider baselines, some more than 1000 kilometer, DGNSS and S-bus. RTK, they are very accurate up to 10 centimeter and 1 centimeter to 10 centimeter level, shown in blue color here. And but their baseline is very limited within 100 kilometer. But PPP, you can see they give from 5 to 10 centimeter level accuracy somewhere, and it is a global, not dependent on the baseline. So now coming to satellite navigation applications using GNSS systems. So you can see in ancient time, people were plowing the field using bulls, and there was a lot of effort from the farmers, which was to be done in this kind of traditional farming. But now there are tractors equipped with GNSS correction parameters from differential or PPP services, and they are also equipped with sensors which can sense the soil, and uh, then uh, using position accuracy, they can drop the seeds at 10 centimeter level distances, which is very economical, as if you spread the seeds randomly, you will require more seeds. But with this GNSS technology, I have to put the seeds at every 10 centimeter in multiple rows. So it gives good yield, as well as less seeds are required during the season. Then I will cover one classic example of precision agriculture, or we call as smart farming as well. So as I have described, we can put seeds in every 10 centimeter level accuracy, or better if we use PPP or differential positioning. So, these tractors or equipments are equipped with a lot of sensors. They are now AI based also. So they are using various different techniques to do the smart farming. They analyze the yield. There are statistics available. So using all those tools, big farmers with big farms are using these services abroad, and in Punjab and other places where they have very big fields in India. So right now Mahindra has taken initiative to develop this kind of tractors, and uh, people are using those kind of facilities. Now coming to one example which all of you might have used. This is a GNSS application in Ola and Uber cab services. All of you might have used Ola and Uber at some point of time. So how it works, this satellite-based navigation systems are responsible for providing you this kind of service. You need to switch on your location in your mobile. Your mobile is having a GNSS receiver chip, and when you switch on your location, you download the app of Ola or Uber. Then your location goes to their server, and then they suggest you nearby drivers or cabs available. And then using AI based algorithms, the driver will come exactly to your place using shortest routes. So this is one kind of application. It's very fascinating, and everybody is using right now. So in at least in metro cities and bigger cities. So if we can't imagine our life without these services now. So this is possible because of very accurate uh, positioning and maps available, and people can reach to you without calling you where you are. So it's a great thing, and similar kind of a lot of applications are being developed. And as I've described in my first slide, we have done some machine learning applications using Navic or GNSS signals. So there are signals which come to the receiver almost directly. We call them line of sight signal. Some signals are obstructed by buildings, foliage, or forests, or some other things, obstacles. So we call it non-line of sight signal. They reach to the receiver with very difficulty. And there are multi-path signal, which are somewhere between the line of sight and non-line of sight signal. Multi-path is when signal comes to the receiver from the multiple paths, not directly. So it's because of the reflection from the some present reflecting bodies. So we need to categorize these signals in different categories, whether it is line of sight, multipath, or NLOS, non-line of sight. So we developed some deep learning, machine learning and deep learning models using clustering techniques. You can see in the picture how beautifully these signals are being classified. So using machine learning, we are doing this kind of application. And recently, we have attempted one application to predict ionosphere using LSTM model, long short-term memory machine learning models. So we used here very first time Adit L1 data also, because Adit L1 is at Lagrange point L1, and it is capturing the solar radiation from the sun. And you know, ionosphere variability is responsible is due to the fact that solar variations are coming to the Earth's surface, and even before they interact with the ionosphere and make it vulnerable while we do positioning. So we use long short-term memory models, and we predicted the TC very accurately. So you can see in the graph actual versus predicted. So when we do not use Adit L1 data and predict ionosphere, our percentage accuracy is 27%, but when we include Adit L1 data with LSTM model, 20% more improvement is there, which comes down to 7%. So these kind of models we are using for scientific applications, and this has a lot of bearing on removing ionospheric content. Now coming to, as we know, GNSS does not only give position, it also gives timing and velocity information. So there are timing receivers we are developing. They are responsible for synchronizing the grids. And you right now, children and people play video games synchronized with the people sitting in other countries. So those kind of things are possible because of very accurate time synchronization using GNSS systems. And now one more application I will cover is Navig messaging services. Some of the satellites which are not useful for navigation purpose, we have a messaging system in our Navig design. So using those messaging facility, we can provide services to the fishermen which are in any kind of distress, and we rescue them also sometimes. So this is one very important application for marine environment. Then Navig is coming in chips and mobile phones as well. So more than here I have written more than 6, but now I know more than, I think, 12 or more GNSS chips which are accommodating Navig L5 signals. And Qualcomm and other companies have taken initiative to put Navig signals or integrate Navig signal also in their chips. And right now a lot of receivers are giving the services using Navig along with other constellations. As I've told, it's an era of multi-constellation satellite or receiver chips. So, and one more thing I will like to emphasize here, in 2016, Google has developed one app. Earlier, mobile phones or smartphone devices were giving only lat, long, and altitude information. However, after this app came from Google in 2016, we can tap raw measurements from any smartphone device, and people are studying those signals, those measurements from smartphone devices, and studying multipath effect, then position accuracy, then differential positioning. A lot of things are being done using mobile phone data. So every mobile phone or smartphone devices have become GNSS measurement devices. So it's a great revolution. This I have covered, so I will skip that. Now coming to, as I've told, we have developed pseudo-light-based navigation system for aviation applications. So right now this is part of uh, this reusable launch vehicle program of ISRO. So this is the timeline how we developed the system. We started in 2016, and now in 2023 we successfully did first landing of RLV, which we call RLV LEX experiment, which is the landing experiment. So in that RLV vehicle was dropped from a defense helicopter at an altitude of 4 kilometers around, and then it autonomously landed on landing strip near Bangalore, Chitradurga, and we used to go there and deployed our system there. It's a ground-based navigation system. Now next phase is orbital re-entry phase. In that there will be launch from SHAR, Sriharikota, and the RLV vehicle will be in the orbit for some time, and then it will take a entry in Earth atmosphere, and then it will land automatically the way we have done in our LEX experiments. So these are the some hardware we have developed, and this picture is the picture of pole. So all the transmitters are uh, uh, on the foot of this pole, and the signals are getting transmitted from this antenna here on the top of the pole. So using these transmitters on pole, these are satellites, but they are not revolving anything. So we call it as pseudo satellites. So they transmit the signal, and signal is received by the receiver inside the RLV. Then it gives RLV location. So using that, we did successful landing. Here you can see in this picture. In LEX 1, we have got around 13 centimeter measured accuracy on the airstrip. Then LEX 2, 35 centimeter, and LEX 3 even better, 10 centimeter accuracy we have got. And this middle picture is actual picture of landing. You can see there is a video available on YouTube, all the 3 LEX missions. So we are proud to be part of this whole system. This system was fully developed and designed in SAC, Ahmedabad, and this is among 4 or 5 countries. We are among 4 or 5 countries in the world which who have developed the system. And this system I recently proposed for lunar navigation. So I'm working with the NASA, European Space Agency ESA, and Japanese Space Agency JAXA in close circle under United Nations umbrella. So there we have proposed this kind of system. So before that, I'm coming to one more GNSS application, which is very getting very popular nowadays. It's a LEO PNT or LEO Doppler PNT. PNT is position, navigation, and timing. So here, as I have told initially, LEO satellites are very close to the Earth, somewhere you can say 600 to 1200 kilometer range. So due to proximity of Earth, they transmit some signal uh, whose received power at receiver is around 1000 times stronger than GPS or any other satellite signal. So because of their high received power level at receiver and large number of satellites, and they are moving very fast, it is very difficult to jam these signals. So so as you know, all the systems are getting developed because of some defense requirements or national security requirements. So right now defense people are seeing this as a very lucrative option over GPS, because GPS signal is very very feeble or faint when received at the receiver. So any jammer which can transmit more than that signal power, it can jam the GPS signal. So defense people are very apprehensive about this weakness of GNSS signals. So they are trying to develop one LEO Doppler based PNT where this kind of vulnerability is reduced to some extent. We cannot say it cannot be jammed, but it is difficult to jam. So defense people are seeing it as a very better option or GNSS which is vulnerable to jamming in some war situation or any other adverse situation. However, challenges are these are fast moving satellites and more satellites will be required to track. We can have here position using a single satellite or multiple satellites. There are variants. So if we are using single satellite at multiple instances, I cannot get position at every second because then satellite geometry won't be changing much. However, if I use more satellites, so this satellite is visible for 10 to 15 minutes to a user because they are moving very fast. So we need more number of satellites. So this constellation can have more than 1,000 satellite to cover the whole globe. So we are doing a research and development activity at SAC where we are trying to design this constellation and develop some prototype receivers which can receive those signals and be of some use to the required community. So this is how we are designing this constellation. On the right side, you can see there are a lot of 1200 satellites around and they are visible to a user and more than 60 satellites are visible, but they are coming and going. They are visible for 15 minutes only. So here we don't require precise ranging code, atomic clock as well. We know the Doppler content in the signal, and using that Doppler information, we can process different kind of advanced navigation algorithms, and we can get good position accuracy. In the graph below, I've shown achieved position accuracy from meter to centimeter to meter level using extended Kalman filter. Blue line is position accuracy achieved through Kalman filter, and red is without Kalman filter. So Kalman filter provides you a very stable and smooth position. This is for a static receiver. We are developing variants for dynamic receiver also. So a lot of work is going on in this direction, and it's a very upcoming domain which people are working right now. Now, in the last segment, I will cover this lunar PNT. This is one of our favorite things right now. So, India has proposed pseudolite system for lunar PNT, and ISRO is considering to deploy a pseudolite transceiver. How we will deploy there? Here, I have shown you a pole, which I can survey that pole location, and I can deploy our transmitters. But how we will deploy on lunar surface? It's a big challenge. So we are considering to use our landers only. In the lander itself, we will put the transceiver because there is no surveyed location. Nobody is there to deploy a pole after digging the lunar surface. So these are few challenges which we don't envisage or see on the Earth surface. Here, a lot of things we can do manually or using the machines. There, nothing is available. So in the absence of any radio navigation system on moon, pseudolite is one of the most feasible option for lunar PNT as it can be easily deployed on lunar landers. And we have, if we have 3-4 such landers with transceivers, we can do some positioning. So a common framework we are developing with other space agencies under United Nations umbrella to make it happen, because one country can send one lander not very frequently. So suppose I have sent one lander with one transceiver, then another lander, if it goes after 5-6 years, one lander uh, 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 may not be useful at that time. So or usable at that time. So we need simultaneous landers there. So that is also a problem. So either you do a launch in which more than 2-3 landers go in one go. So that is very difficult and nobody has achieved. So we can work in collaboration with other space agencies and make it happen. So the challenges are of different scale on lunar surface. So this is the salient feature of pseudolite system which we are proposing. In the right side, you can see 3 or 4 transmitters and 1 rover to whom we are providing the service. Some rover which go with the lander, or some robots which will go in future, or some moon nodes like astronauts. We will be having moon nodes in future. So they will travel through the lunar surface, and they will be requiring this position, navigation, and timing information. So this pseudolite system is a local area navigation system. It covers say 10 to 15 kilometer range, but the system uses bidirectional ranging, so it is autonomous, it is self-calibrated and self-synchronized. I'm not elaborating on the things because it's difficult to grasp everything in very short time. So I'm just mentioning the main features. You can download some papers. Some of my presentations are there on Google or internet. You can Google them and find them. So using this and some AI based path planning of rover can navigate using position information from pseudolite system. So some of the simulations we have done on such systems toolkit software which provide us lunar environment to simulate lunar environment. We have simulated those environments with 3 pseudolite transceivers and 5 pseudolite transceiver geometry, and we have got meter to sub-meter level position accuracy. Here we have not corrupted measurements with any kind of errors, though some errors will be there. But the good thing is that on lunar surface there is no ionosphere, no troposphere, there is no atmosphere in fact. But some people say that because of solar flares, some of the ionosphere content might be there in exo uh, um, sphere of the moon. So those kind of research are also going on. So, but pseudolite system, as I've told, it covers only some 10 to 15 kilometer range. So we cannot cover the whole lunar surface. So in future, we are ISRO is planning to make or develop a system which is satellite based system as well as pseudolite based system. Means it's a hybrid system where there are satellite component also, and pseudolite is on the surface on the landers. So using this kind of combination, we have a very good volume from the space segment of the satellites on the moon and on the surface using pseudolite. So if volume is more, our PDOP will be less. As I've told, volume is inversely proportional to PDOP, and we require less PDOPs to get better position accuracy. So we have proposed 8 to 10 satellites in 2 elliptical lunar frozen orbits. There is one more problem. On Earth's surface, our gravity is very uniform almost, except on equator. However, on lunar surface, there are variable mass concentrations, and because of there are very huge craters on the lunar surface. On the Earth surface, there is a environment. So if any crater, any asteroid or something comes to hit the Earth, they are burnt in the atmosphere. But on the lunar surface, there is no atmosphere. That's why you see a lot of black patches there. They are craters of hundreds kilometer long. So, so because of these uneven terrain on lunar surface, we don't have uniform gravity there. So we need to develop new models, gravity models of moon to have very accurate positioning services. So these works are going on. We are doing the simulations, and we are in phase of designing how we can make our satellites, in which orbit they should be, and what kind of gravity models, reference frames, and orbit models we require on lunar surface. It's an entirely new domain we are working right now. This is my last slide. As I told you, the things we are doing, they are not up to theoretical level only. Recently, two missions have happened. One in February 24, one lunar mission, lunar lander landed there, and one intuitive machine company is there of US, which has developed a pseudolite kind of RF beacon, and the picture is shown here as lunar node 1, we call it. NASA has developed this payload with intuitive machines as a private vendor. So using that, they have successfully deployed this beacon on the lunar surface last year, and this provided very useful data, and NASA people have analyzed this data and they have published papers you can get in on internet. Second, right side part, this has very recently happened. This is called LUGRE mission, Lunar GNSS Receiver Experiment Mission. People now believe that, or with LUGRE receiver, they have successfully received Earth GNSS signal on Moon. They are very, very weak signals. They have used very advanced navigation processing algorithms of weak signals on lunar surface. So they have launched a lunar mission, and it successfully landed on Moon. It is called Blue Ghost of NASA, and it landed on March 2nd this year, 2025. And this has given very nice data, and this receiver was developed with the collaboration of NASA and one Italian company, Quascom. So they have the world record of fixing GNSS position uh, at unprecedented distance of 410,000 kilometer on lunar surface. So from Earth, more than 4 lakh kilometer distance, they using Earth GNSS satellite like GPS. This is a GPS and GLONASS receiving system receiver. So using that GPS and sorry, not GLONASS, Galileo. GPS and Galileo signals, L1 and L5 measurements, they have fixed the position on lunar surface more than 4 lakh kilometers from Earth's surface. So with these two missions, which were successfully landed on lunar surface, they have shown the way forward that we can have uh, this kind of navigation systems in future. So ISRO is also trying to develop these kind of sensors, deploy them through the landers there, and in 2030 time frame, we are hoping that some of our systems will be there to show us the path ahead. So that is how we see the navigation applications from Earth to Moon and then Mars. So our wishful thinking is to colonize Mars. So there is no spacecraft or any rocket which can go from Earth to Mars. So Moon is very important because they are trying to have Moon as a launch pad. They will go first from Earth to Moon. They will refuel the rocket, and then they will travel to the Mars. So, and second reason why Moon is important is that there are a lot of minerals there which can solve our energy problems. So people are exploring, scientists are seeing the data, they are seeing the soil samples which have been collected in Apollo and other missions by US and other countries, Russia. So a lot of exciting things are happening. So these are some of the references. I've referred these books and made the designs in our receivers, in Navik receiver and then pseudolite receivers, and we are heading towards Moon now, so, and Mars in future. So these are some of the books. First one is from Pratap Mishra, then Kaplan, and then Petrovsky, and some other books are also there. So you can go through them and learn GNSS. So I will end this lecture with the quote that the winds and the waves are always on the side of the ablest navigators. It is a quote by Edward Gibbon. And with this, I thank you for patiently listening to me. And this is my email ID. If you have any doubt later on or you want to contact me, please don't hesitate. And if there are some questions, I can take up now. Hope I have not exceeded my time.
Thank you, sir.
Any
Thank you, sir.
question? Yeah.
Any questions from participant?
Yeah, myself, Dr. Kavita. Good evening, sir.
Yeah, good
Sir,
evening.
I have one doubt. Sir, what is the status, sir, NAVIC status, sir, presently?
Navik, as I've told, it's a constellation of 7 satellites. However, we have done more than 7 launches, but last launch of NVS-02, it was partially successful and satellite couldn't go up to the desired orbit. So it is partially useful only. So we are not considering this as part of our constellation. And one H Navik 1H earlier was not successful. Launch was not successful that time. So with these two, launches which were not successful, we have sent more than 7, 8 satellites there. However, due to some issues in atomic clocks and aging of the satellites, every satellite has
Yes.
some fuel through which its life is decided. So right now situation is we have 4 working satellites around, and some new launches are going to happen in 2026. I think at least 2 launches are proposed. So with that, we will be having 6, or in coming years 7 satellites. So uh, right now we are having 4 satellites because of some of these issues and some failed launches.
Okay. So
So
because
I
we are
hope I
receiving
answered
4
your question.
satellites,
Yeah.
okay. To get position, minimum 4 satellites are required. But sometimes what happened, this because of the signal loss, we are unable to get the position.
Yeah, you are very correct. But as I've told, nobody is processing any constellation alone right now. So I think
Yeah, yes.
we have some respite.
Hybrid mode.
Yeah, yeah. So in hybrid mode, every chip is having all other constellations also.
Mm.
So, but Navik is coming up, and there were some setbacks. This happens when you design and launch the system satellites and make the system. So Galileo, when it was developing its own system, first 4 satellites they termed them as test satellite only, not as part of the original constellation. Because why? Because they had a lot of new things, new kind of signals after learning from GPS and GLONASS. So the first 4 satellites were test satellites. They measured the performance, and then they launched the actual constellation satellites. So India did not go in that way, because launching 4 satellites and making them test satellite only, it's very costly business. So and since our system was regional system, so we send all the satellites, and you will be surprised to know, some of you might be working with those signals. Its accuracy is at par with the GPS system, which is working since last 30 years. So we were successful in giving performance, however, maintaining satellites in space, and there are other things, atomic clocks and many other things are there. So every satellite should be equipped with atomic clocks, and India was earlier dependent on foreign parties for commercial atomic clocks. Now ISRO has developed their own clocks. In NVS-01, our indigenous clock has flown, and it will be part of upcoming launches as well, satellites as well. So it's a trade-off of different things. So we are coming up strongly, and um, we are satisfied with the system we have made. Only we need to increase the launches so that original constellation of 7 satellites should be intact.
Thank you, sir.
Yeah, most welcome. Any other question? So if there is no other question, I think we can stop here. I hope you enjoyed the presentation, though time was very short. I had to cover a lot of things. So thank you for your patience and listening to me.
Thank you, sir. One vote of thanks, sir, please.
Thank you, sir. On behalf of organizing committee, it is my privilege to propose the vote of thanks of today's session. At the outset, I extend our sincere gratitude to our esteemed speaker, Dr. Ashish Kumar Shukla, for delivering such an enriching and inspiring talk on the overview of SATNAV applications. Sir, your session has provided deep insights into India's remarkable progress in satellite navigation, especially through programs like Gagan and Navik. The way you connected the current capabilities with the emerging concepts such as pseudolite based lunar PNT, machine learning enabled navigation, and GNSS innovations was truly engaging and thought provoking. We are grateful for the time you took to share your expertise with us late in the evening, and we truly appreciate your commitment and support to this faculty development program. Your words have undoubtedly broadened our understanding and encouraged us to explore new research avenues in this evolving technological domain. I would also like to express our thanks to all the dignitaries, faculty members, research scholars, and participants for joining us and making this session meaningful. A special appreciation goes to the organizing team, coordinators, and technical support staff for ensuring the smooth conduct of this program. Once again, our heartfelt thanks to Dr. Ashish Kumar Shukla for gracing this session with his knowledge and presence. Thank you all for being with us this evening. Wishing everyone a pleasant night ahead. Thank you.
Thank you, madam, and I again will thank organizers and Dr. Mukesh, who uh, contacted me to deliver this lecture. It was great to be part of this lecture here, and I think you could get some of the very advanced things we are doing here, and so navigation is a very interesting field, and I hope some students might be there. They will take up some of the activities in future. So thank you all.
Thank you very much indeed, sir. Thank you, sir.
Thank you.
So we will close the session, sir. Today's session.
Yeah.
Thank you. Thank you, sir. Everyone, please fill the feedback form. And for the tomorrow's session, everyone please join by 6 p.m. exactly. Thank you. Thank you all.